Hi everyone, my name is Deirdre Larkin with Atkins Ireland, and I'm here today to present my talk on the development of a hydrogeological conceptual model for the Water-Rock urban expansion area in East Cork. Atkins was appointed by Cork County Council to undertake the preliminary design for key infrastructure required to meet the future housing development plans for the general vicinity of Water-Rock urban expansion area. So I suppose the key infrastructure would have included new links, new surface water drainage, realignment of existing roads, a new wastewater pumping station, new rail stop, and other infrastructure. And I suppose as many at the conference today are more than aware that this area of East Cork is underlain by Karst geology. So that was one of the, I suppose, initial constraints of the project, which would have informed the preliminary design. And we had, I suppose, two surface water courses within the vicinity, Water-Rock stream and the Onacurra River as well. So I suppose at the very outset, I suppose a preliminary design stage, and I suppose to feed into the flood risk assessment, we needed to have a clear understanding of the surface water, groundwater interactions in the vicinity, and I suppose particularly in the context of the Karst baseline setting. So in order to do this, we need to develop our conceptual site model. So we followed three broad tasks. The first was a desk-based study and site walkover. The second focused on water level monitoring, rainfall level monitoring, flow monitoring and tracer testing. And then the third then relied on geophysical survey methods at key locations, accessible locations within the study area to see if we could get a better understanding of the any subsurface features within the vicinity. So this is the site setting. So in terms of land use, primarily agricultural, some industrial and commercial land use in the southern portion. And then we obviously have a Water-Rock stream flowing in the western portion of the site and the Onacurra River in the eastern portion of the site. In terms of topography and inferred groundwater flow direction, so the western portion of the site would drain pretty much to Water-Rock stream and cave, while the eastern portion of the site would drain to the Onacurra River. There is a spring just immediately south of the site and the N25 called Banshane Spring, which feeds Banshane stream, and this stream then discharges to Dungorney River further southeast. And I suppose just looking at this slide here, you know, we can see that there's obviously a gap. So I suppose Water-Rock stream discharges to ground and disappears to ground at Water-Rock Cave and Swallow Hole. And then obviously we have a spring further south. So I suppose the first of all question was, are these linked? Are they connected? And there, when we did our desk study, there was anecdotal information to suggest that possibly they were. In terms of soils, the subsoils beneath the vicinity are primarily till with areas of gravel, and I suppose gravel would be obviously key for groundwater storage. And then in terms of geology, we have the Wilsortian limestone formation, and the Cuskinny member of the Kinsale formation, and then the Ballysteen formation as well. So here are the two karst features, Water-Rock Swallow Hole and Cave system, and then obviously the spring at Banshane further south. So in terms of flow monitoring, we had three primary locations, upstream monitoring locations prior to Water-Rock stream going to ground at the Cave and Swallow Hole, and then downstream flows were measured at the Banshane Spring, and also further downstream at Banshane Stream. So I suppose the flow rates from the upstream monitoring location range from approximately 400 to 1,200 meters cubed per day. At the downstream monitoring location at the spring, we had flows of 0 to approximately 90 cubes a day. And then further downstream at Banchain stream, we had flows of between approximately 500 to 2,300 cubes a day. And I suppose it is worth noting that all of these rates and flow monitoring data was measured during June and July of 2018. So obviously during the droughts, they would be indicative in terms of upstream flow rates of groundwater-based flow to the Water-Rock stream. So I suppose the flow monitoring didn't provide any further clarity. We looked at tracer testing. So we did used a dye tracer. So dye was released at the upstream monitoring locations prior to discharge to Water-Rock Cave and Swallowhole. And subsequently then the two downstream monitoring locations were observed and no dye was noted. This was followed with the installation of a catching system to the south downstream monitoring locations, and then at the upstream monitoring locations, biodegradable floats were released into the system, and the downstream monitoring locations were monitored for 48 hours subsequent to this, but the floats did obviously not come through at these locations. And then another series of tracer testing was carried out. So a composite sampler was installed in the downstream locations, and upstream dye was again released, and then samples were taken at the downstream locations every 30 minutes for 24 hours. And these samples then were subsequently checked with a UV lamp, and no dye was observed. So again, I suppose the tracer testing proved inconclusive. So this brought us on to our geophysical surveys. So the 2D res survey, we carried out two sections, so ER05 and ER06. And I suppose the siting was a function of accessibility, permissions, and also I suppose kind of key locations between the Water-Rock Cave and Swallowhole, and then the downstream Banchain spring and stream. So the survey results were quite interesting. So ER05, which is the section here, and you can see across the results, the output, that the three possible locations where karst has been identified. So, so karst zones, or potential karst zones, were identified just at the edge, so at the eastern edge, the central portion of the section, and then again on the western edge or portion of the section. So three possible karst zones, not just one. And then when we look at the results for ER06, which is further south prior to Banchain Spring, no potential karst features were identified in the subsurface based on the 2D res results. So I suppose the key conclusions arising from the various site assessments undertaken, I suppose first and foremost, potential underground karst identified at the ER05 section, which was the most southerly section to the Swallowhole and Cave, but not along section ER06, which is further south and just above or north of the spring location. So I suppose ultimately it's unlikely that the Water-Rock Cave system is linked to Banchain Spring via a single karst conduit or a straight line. Any potential connectivity is likely to be complex and may involve groundwater discharge to other karst features within the vicinity or surface water features in the wider area. And there are a good few potential options, you know, or scenarios that could be occurring within the vicinity. So I suppose looking at all of the information based on our desk-based review and our site assessment, we derived our hydrogeological conceptual site model. And I suppose it's important to note that this is not specifically just for the UEA study area. This extends to the groundwater catchment. So this encompasses a far wider area, reaching to the northwest of the site of the uplands in that vicinity, and right down then to Water-Rock stream. So the entire area is underlain by low permeability tills and gravels. Groundwater levels would be anticipated to be less than 10 metres, with a seasonal fluctuation of 5 to 6 metres. And I suppose there's two key groundwater zones. The first is the gravel aquifer, which has an important function in terms of groundwater storage. And then the second, obviously, is the bedrock aquifer, the regionally important Karst limestone aquifer, and the sandstone and limestone aquifer as well. So rainfall recharge will obviously be a function of infiltration capacity. So areas where we've got poorly productive bedrock overlain by low permeability tills, you know, but we'll obviously see far less infiltration. And then areas where we've got the gravel aquifer or exposed bedrock will see higher infiltration rates. And I suppose our conceptual understanding was that groundwater discharges to Water-Rock stream via the gravel and bedrock aquifer and provides base flow to the stream as evidenced in the flow monitoring data during the 2018 drought. So I suppose all of this information fed into the design criteria and how we dealt with the karst conditions within the preliminary design. So I suppose there's a few kind of key concepts that underpin our understanding of the system. So I suppose when the Water-Rock stream is lost to ground at the swallow hole or cave at Water-Rock itself, the underground stream enters a complex karst cave system. Not to state the obvious, it probably continues generally south, but not in a linear direction directly to Banchain Spring and stream. So hydraulic connectivity between the known karst features of Water-Rock Cave and Banchain Spring further south is complex with a range of potential scenarios at play. So to inform the project-specific flood model, the groundwater contribution to Water-Rock stream was estimated prior to being lost to ground at Water-Rock, swallow hole and cave. And I suppose this was based on the understanding that, you know, in terms of SUDs, that the surface water runoff rates were designed to match existing greenfield runoff rates. So there will be no change. And then groundwater calculations for the catchments, the surface water catchments, were based on groundwater recharge rates in areas within those relevant catchments. So taking account of land cover, infiltration rates, and areas as well as the local geology. So base flows of between approximately 280 cubes a day and 4,200 cubes a day were estimated for each catchment area. And I suppose those numbers are quite far apart, and a fundamental explanation for that is the fact that catchment B, which had the larger groundwater base flow, has a sizable portion of gravel aquifers within that vicinity, whereas catchment A has no gravel aquifers within that catchment. So then, based on our catchment and the calculated base flows, we were able to use calculated rainfall rates for flood events to determine groundwater flows during rainfall return periods. And I suppose we did this for a range of scenarios. And I suppose given the uncertainty in terms of the karst setting of the site, and then also the added complexity of what we knew and what we didn't know in terms of the geophysical survey results, and the fact that we know the karst is obviously a play in the area, but we don't know the extent of that system. So we adopted a conservative approach. And so, you know, a worst case scenario was incorporated within the actual design. And so the infrastructure in terms of drainage was designed to provide sufficient capacity in a worst case scenario, a 1 in 1,000 year flood event. So thank you very much for your time. I'm happy to take any questions if you have any. Thank you.